guessed that complicated process is conflation. It's called conflation. It's going to be the last thing we're going to talk about today. If you don't know what that means, don't worry. We're going to see the definition and we're going to see the different types and how it is applied to the problem that we're going to see. So with that, let's see what is Remix about. If I had to summarize Remix in one sentence, this would be it. What we try to do is to bring together the complete transportation picture in a single software platform. That means that we have different models. We have a transit planning model, a street design model, a mobility management model, all of them with very specific functionalities to those use cases. But as you see, all of them very literally actually are based in this yellow big rectangle that is data. Because even if you have the perfect functionality that you need the context and you need to actually make an informed decision on what you're doing. And with that, I'm going to show you a bit what this means in Remix by showing you in a quick demo the transit planning model and the explore data model so that we can start to understand, put into images what I'm talking about. If you haven't seen Remix before, this is it. This is a big part of it, actually. It's a map, very clean. This is the part we call explore. So in this map, you see there are very few bottoms. For now, we're going to ignore the left part. And on the right part, you'll see that I have two bottoms. Both actually say explore. I will start by creating a polygon, very random polygon, around the city center of Philadelphia. And you'll see on the left that I get a list of statistics. So if I'm a planner and I want to know what's going on in this part of the map, this is a very easy way. I get statistics about the census data, about how many hospitals there are, basically about anything that is loaded here. This is something that you could do in a GIS software, but it's much easier to do it like this. You don't need to open any layers. Everything is already there, even if you don't know how to use it, or you're not a technical expert in ArcGIS or something like that. It's easy to understand. If you have worked with this kind of thing before, maybe you've guessed what we're doing here. We're intersecting this polygon with everything that lives in this part of the map, and we're getting all the information we can from it. In the same way, if you actually want to see that information, like population, you can always go to the layers and open them like in any other GIS software. You can always rescale very easily to the part that you're seeing, and you could even compare with another census or compare two polygons in different points in time to see how, in this case, the population changed in these 5 years. The last thing I'm going to show you is a use case. Let's say the last thing I'm going to show you in Explore, sorry, is let's say that you're analyzing how your bike lanes are doing in the city. So you might have your bike lanes layer, and you want to see how many crashes are happening near your bike lanes. To do so, I'm gonna pull out now a very similar tool. But what we're doing now is selecting the bike lanes that I want to analyze. If I zoom in, you'll see that I have a buffer around each of these bike lanes that I selected. Actually, I can change that buffer to whatever I want if I wanted to do an analysis, a demographic analysis. But now that I'm working with collisions, I'm going to keep it tight. And now maybe I want to see which of these collisions happen in those buffers, so I can pull them out as well. Now I can see it visually, or this is actually very new, and I love it. I think our engineers made a great work on this. You can see here, you can break down the data, in this case collisions, and understand what is going on for each of the years, understand what was the severity of all the accidents that happened near the bike lanes in the buffer that we're selecting here. Even so, you could actually filter by different types of bike lanes and see how many of these collisions happen in a conventional bike lane and how many of them in a paint buffer bike lane, for example. You can always export this, and it's basically very, very easy to query your database, your whole database of Philadelphia in this case. To jump into more transit-specific use cases and start introducing the problem that we're going to talk about today, let's go to Brooklyn. So here in Brooklyn, we have a line. This is a transit line. This is the transit-specific model for Remix. You see that on the left, I have a few new things like the timetable, the frequency, more information related with transit specifically. I could have the cost. I know I'm not showing it because it's not the subject that it's private, but we also have all the possibilities of intersecting the data that we have from transit with all the information that we had from population, minorities, and all of that. The layers are still living here. And we can do all the same things we did before. But as a planner, and let's think about COVID, when COVID came, all the demographic analysis passed to a second plane, I would say. And the priority was to make sure that the buses were not too crowded, make sure that the people who had to take the bus could take it safely, and respecting social distancing measures and all of those things. So in that case, what a planner would like to see is boardings and alignings, how many people is boarding the bus. To see that kind of thing, this is what we had at the time. This is called a ridership layer. That's the style that we have and how we call it. And what this layer is showing is how many people is boarding the bus on each of the stops, and how many people, you can totally hear from the right, is getting off the bus on each of the stops. You can actually put the mouse there. You see I have a number of alignings, a number of boardings, total activity on the line. So this is telling me the activity on the stop, but it's not telling me how full the bus is at each given moment. So if the question is, how full is the bus in this segment, or for that sake, in all this part of the line, for example, it's not that easy to answer. If I really, really want to answer that question, I would need to sum up all the boardings until this point, for example, and subtract all the alignings until this point. And like that, I can know how many people is on average on that bus, and if the bus is too full or not. So this was the problem that we faced as a software company, I would say, during COVID. Our customers had the data, but were not able to answer the right question for that moment. And this is actually something that happens a lot. Most of the PTAs have all the data they need. They already have it in-house, or because they have a provider that provides that data, but that data is not ingested for planning purposes. It's ingested for different purposes. In this case, ridership data comes from APC providers or CARIVL that are very focused on real-time monetization, and all their infrastructure and effort in the end is put into making sure that that vast amount of data gets into the system in the right way, and that the operators can make decisions in real time. So I find it very hard to explain how this can be a problem, like having the data but not being able to use it. So to give you a simple example, let's think about Google Maps for a minute. Maybe the best data visualization ever created in humankind, I don't know, that's my opinion. You have a lot of data here, you have all that you want, all the answers that you want, you could say, right? And it's very easy to interact with it. If I want to know how to get from A to B, how long does it take, what are the best modes, even what restaurants they are, it's very easy. But what if I'm a planner? And what I'm trying to answer is, what was the average speed in a given street last month? Or what was the traffic count? How many cars were there during 6 a.m. During the morning peak last month in average? Even if Google Maps has that data, it's not that easy for me to get it. And the reason why that is because it's not designed to do that. It's designed for other use cases, for those that actually are very easy to answer with Google Maps. Well, the same happens with ridership data in most of the PTAs. Ridership data comes in for real-time monitoring, for real-time decisions, operations. And when a planner tries to use that data for mid or long-term planning, he or she finds a lot of obstacles. The first one is that it's silo, the silos of information. Most of the times that data belongs to other department. They have to ask for it. It's work from the other department. It's a whole workflow that is not easy to manage, mostly because you know that your colleagues have a lot of work to do. You don't want to add something on your plate, or even if they have the best of intentions, they cannot do it sometimes. Another problem is that even if you convince your colleague to give you the data, that data might come very disaggregated and raw, and a lot of work has to be put into to aggregate it, make the data quality checks, and all the things that need to be done to make sure that you can actually get an insight from that data. And the third one is, in the case you want to put it on a map and make it insightful, well, most of these sources of data from APC don't really have a geometry like a line for you to put it on a map. So you could create a graph like a heat map, you could create a scatter plot, you could create things like that, but it would be hard to put it on a map. It's a whole new problem that you have to solve. So there are 3 problems to solve. Let's say that you solved the first 2 problems, you got the data, you could aggregate it, you still will have something like this, points, and that's not so insightful when you want to answer the question how full or crowded my buses are. So what we thought at the time is that we could actually take this ridership data that comes for other purposes, doesn't matter, aggregate it. We could do the quality checks ourselves and merge it, combine it with other source of data that has the geometries. In our case, we work a lot with GTFS. For those of you who haven't heard of it, it's a data standard, and it's basically how PTAs put their transit information into Google Maps. So it's very, very expanded. Everyone uses it. And GTFS has information about the times, and it has information about the geometries, basically. So what we did was combine the ridership data that comes plain, comes disaggregated, we aggregated, we did all of that, and we put it into the lines of the GTFS into bus segments. So
we have a question from someone in the audience. I think it has something to do a little bit with that last slide. Question for Santiago: have you explored unifying the layers in any simulation?
When you say the layers, what layers? Some specific layers. We do combine layers. Let me check the question. We do combine layers and create new ones, but they're not dynamically combined. I don't know if that answers the question.
Okay, we have one more then. How do you know, oh, and in the chat said it does, thank you. So you did answer that question. And then the other question is, how do you know bus load if you only get onboarding events if they pay with FastPass and not offboarding events?
Well, that's a problem, yeah. You don't know it. if you don't get the offboarding events. So in this case, we only did it for those customers that had onboarding events and offboarding events. Trying to simulate or model where people is getting off the bus is an experiment that we ran last year. We actually have a blog post on that that I can share with you later, but it was an experiment and it's not something that is in production. So if you don't have the offboarding information, you cannot know the load on the buses with the system that we have today. We're not solving that problem with this. I mean, I'm not going to solve this problem in this talk if you're expecting that.
That's great. That's all the questions for now. Thank you.
Okay, no problem. Okay, so, well, we identified this. We had been hearing about load and crowded and ridership for a while in our community that is called Transport Talk. It's a Slack channel with a lot of transit planners from all over the US and Europe. So we thought maybe we should create a pilot about this. Let's see what people say if they're interested in them. I had to blur them out, but long story short, we got interest from 16 PTAs that send their data almost immediately. These are 12 of them. You can see there are small ones, middle ones, big, very big ones. So what we found out is that it was a need. Didn't matter the size of the company, it was a pain for all of them, for all the PTAs, at least for all the planners. They just had the data, but were not able to use it for planning purposes. We have calls, feedback calls with a lot of them. What we learned basically is that many of the decisions they have to take would be better or easier to take if they could represent some of their variables in segments. And that was a big problem that they were having. They were very successful seeing their data as points, seeing their data as polygons, but not as segments. So that's where we aim. So let me show you how that ended up going in Remix. If you want to know how many people is actually on the bus on a given route between two given stops. After doing all the GTFS process matching that I show you, you could get here in New York something like this. So right now in Brooklyn, this is only for Brooklyn, it's much easier to understand where are your peaks of people. And for that line in particular, I could just filter that one. And it's very easy to understand. You just have to click how many people is on the bus on average, or how many people is taking the bus in average between 6 and 9. So don't get scared about these numbers. These are pre-COVID numbers. I'm not showing the numbers in COVID. But what we see now is what planners actually wanted to see. With this kind of visualization, it was much easier for them to understand where they should put an extra bus, where they were leaving people behind. It was easier for them to explain to the bosses why they were taking the measures they were taking, and this kind of thing. So the feedback we got was absolutely positive. And again, what we learned is that they wanted to see more variables at the segment level. But sometimes, and this is a quote from Carlos Cruz Casas in Miami, he told us that crowding and analyzing the load at the route level was what they needed with COVID. It was a short-term need. But in order to plan for BRT lanes or bus-only lanes, what they need to understand is how many people is using the street boarding a bus. So it's not about what is the route, what are the two stops. It doesn't matter what are the routes. What matters is how many people is using the bus on the street. And that's the argument that you have to make when you're planning a BRT, or that's what you need to identify when you need to understand where to invest on a BRT line. So this is, well, I won't say post-COVID because COVID is still happening, but this is an effort that took place in the last few months that is basically trying to answer another simple question that was very complicated to answer. And is how many people is using the bus on a specific street between two other streets, like first and second. So to see how this is a hard thing to do with the visualization that I have right now, I'm gonna go to Miami in a particular place. And I'm gonna show you the equivalent layer that I had in Brooklyn. Okay, it's taking a second. What this layer shows, again, is load per bus segment, per route. I'm looking at all the routes at the same time right now. And let's check, let's say that I want to answer the question, how many people is taking the bus in this segment over here? Do you see my mouse? I hope you see it. So to do that, I can come here and see how many people is taking the bus on this segment. But let's take a look. This is a bus segment. And what I'm seeing is that it's very, very long. It goes from stop A to stop B. It just stops where the next stop stops. A lot of stops in that sentence, but okay. And what I see here, if I actually click the second one that is on the west, I see that these two segments overlap. So this is a problem, and this happens a lot with bus segments. Bus segments can share the same street, but they're not actually the same. So if you want to answer the question, how many, actually not even how many people is using the bus on this street, but how many buses are going through this street, it's not that easy. It's not that easy from the visualizations we have right now. So what we need to do now is, instead of going to the route and the segments of the route, we need to go and take all the variables directly to the street level. And for that, I'm going to come back to the presentation. And this is where conflation comes in. Actually, we have been showing different types of conflation until now, but this is where it got complicated, the way to answer the simple question. For, well, I'm going to pause here. I'm just going to read the definition so we can start talking about it. In GIS, conflation is defined as the process of combining geographic information from overlapping sources so as to retain accurate data, minimize redundancy, and reconcile data conflicts. Redundancy is exactly what was going on with our segments there in Miami. Also overlapping, they were overlapping. So we had all these conflicts. How do we solve them? By doing this, but it's a problem to do it. Also, if you think about it, what we were doing before with the polygons and all of that falls under the umbrella of conflation and the byte lengths. But it's just a different way from what we're going to see now. So there are different types of conflation. And here I want to give a shout out to our co-founder that actually explained all of this to me not so long ago. There are different types. You have the spatial type, the semantic type, and the hybrid type. Spatial is basically what we had seen in Remix before. You have a polygon, you ask yourself how many points fall within that polygon. You have the area of your buffer, the area of a census tract, what is the proportion of the areas that overlap. This kind of thing falls under the spatial conflation umbrella. You have semantic. Semantic has to do with the common key synonyms that you can find between the two data sets, or even the distance between two texts, right? Like, for example, transit and transportation can be the same, this kind of thing. This is, in most cases, what we did with the GTFS conflation that I was talking about before. Why? Because the APC data had trip IDs and stop IDs, and these fields are something that you can also find in the GTFS. So in the vast majority, we could say it was a semantic conflation after all the aggregation and all of that. And the third one, that is the hard one, is the hybrid. And in this case, what I'm showing here is a screenshot from an Uber talk. Karan Parikh, an engineer at Uber at the time, gives a great presentation on how this works. If you are interested in the deep details, I recommend that talk to you. Not, I'm just going to explain it very briefly to explain what we did. You can think about this type of conflation as the one being used with GPS points. When you get a read from a GPS, this GPS is not perfect. It doesn't tell you in what street it is. You have to guess it somehow. So if you think these red points are the GPS points, you need to understand, in this case, Uber needed to understand what was the path that the car followed. And in this case, it's not that easy as to just say, what is the closest street? Because there could be two, there could be three, you don't know what is the error of the GPS, you need more context. So what these kind of algorithms do, the hybrid ones, they take the whole context. They take the whole story of the points, the whole story of the track, and they optimize for the group. And they say, this is the most probable path. When we talk about this kind of thing, we talk about map matching. And in our case, what we had to match were not GPS points, were transit lines. So what we did was treat the transit lines as GPS points and try to get to the result that we have below. The gray grid represents the street, and the color lines represent bus lines. So we don't care about bus lines anymore. What we want is to have the information at the street grid level. So let's see a bit of what we did. So this is how it works. I'm gonna say a few things here about how it works. It's not gonna be detailed, but the important thing here is that there are three things that this algorithm does. And when I say this algorithm, I'm talking about the hidden Markov model, Markov map matching. This is a paper from Paul Newson and John Crum that is like the Bible in this kind of thing. When you talk about map matching, I recommend this paper if you're interested in diving deeper. It's very, very interesting. And what it does basically is 3 steps. The first step, it takes all the GPS points and it assigns a probability called emission probability or measurement probability that depends on how close the point is to different street segments of the grid. So in this case, point 1, for example, is close to 3 different streets. So each of these streets has a probability of containing this point. And the same thing for each of the other points. Point 2 could be in one of these. Then it analyzes how these points could be connected. So if the column here, the first column is point 1, and it could be in one of these 3 roads, road 1, road 2, road 3, it could go to road 2 or road 1, and it does all the combinations. And it assigns a probability to these transitions. Excuse me. The probability of the transition is, what is the probability that the point 1 goes from the road 1 to the road 1 or from the road 1 to the road 2? That probability depends on the distance. So it takes into account the straight distance or great circle distance, that is taking into account the surface of the Earth, and compares it to the distance that would join these 2 points following the grid of the street, right? So here, for example, I have 2 points, ZT, ZT1. They're connected through the great circle. That's my reference distance. Then I have 2 ways of connecting this through the street or using the street, that is going from the left and the top or bottom, right, top. So the one that is closer to the great circle distance will be the most probable one as a transition. And it does this for each of the points in the GPS tracks. and it optimizes the probability of each of the path and takes, well, the most probable path in the end. After this explanation, I'm not going to dive deeper into this. What we did then? Well, the first thing we needed was the street grid. So we downloaded it from OpenStreetMaps and abstracted in nodes and edges, connect those nodes. We have to tell the algorithm how you can get from each of the nodes to the next one. What are the nodes you need to connect? After creating the graph, we basically destroyed the GTFS lines into points and treated them as GPS points. The good thing here is that all the GTFSs are created by planners. So that means that they draw them by hand, either in Remix, hopefully, or in ArcGIS, or in Google Earth, or something like that. So they're much better than GPS points, are much closer to the streets. And once we did that, what we did was treat each of the lines as a GPS track and match them to the street. In the end, what you got is street segments with variables, and you can play with that. You can aggregate them, and you can basically do whatever you want with those street segments. And this is the result. So if we go back to the map, and we're still trying to answer how many people is using the bus on this segment, with the new output, we don't have overlapping segments anymore. And I have the number at the street segment level. So you see, the question is very simple. And now that I have the output, it's also very easy to answer it. But there was a lot of effort going on to actually get the data set that we needed, or conflate all the information we needed to the street segment. And now it's very easy to answer. And you could make the case much easier for a BRT line. So as we did with the load, we did the same with the speed and everything. So you could actually go now and say, what are my slow corridors? I can only keep the slow ones, for example. There are a lot of slow ones. Just try to keep your mind here for now. Let's see, how do I get out of the annotation now? And now that we know where the slow ones are, we could say, okay, but I want to know of the slow ones, what are the ones that are actually taking a lot of people? And that's the combination you need for a BRT, right? You need to know where are the slow ones, but also where most of your passengers are wasting time because of those being slow. And you can see that here very clearly I have from the west and the north good candidates for BRT projects, for example. And a question that was very, very hard to answer before, now it could be very easy, because this visualization was meant to answer that question. And before, the data was there, but yeah, no one was designing the visualization to do that.
We have a question from someone. It says, can you layer data for multimodal transportation data, which seems crucial for holistic planning? For instance, if a PTA is thinking of creating a bus lane, they probably need to know what the car traffic and possibly bike traffic on the same street segment are like.
That's a great question, yeah. Well, when the question is, can you, the answer is everything can be done. We haven't done it yet, but a similar process could be done for this. Right now, we put our effort on this. We have some layers where you can see the bike traffic or the pedestrian traffic or things like that. But it also depends a lot on what is available for our customers. So the answer would be, we haven't done it yet. It could be done in a similar way, I guess, without knowing the data sets at all, but that's my guess. Okay, if there are no more questions about that, this was all that I wanted to show you for today. I leave here a few references in case you're more interested in learning more about Remix or how PTAs follow a process to identify what are the good BRT candidates. There is a blog from MBTA where they explain this kind of thing very well. The map matching talk about Uber, where they go into the weeds, into how the algorithm works, and of course the paper, where you can find the actual first-hand information of how that algorithm works. And so that's all. I really thank you for your attention.
Awesome. Thank you so much, Santiago. Does anyone else have questions for our speaker? One from Jason here. Jason, I will unmute you. Go ahead and ask your question.
All right. Hey, Santiago. Thanks for the talk. I just was curious what your current areas of research are. If there's things that are exciting coming around the bend that are hot in the mobility space that you guys are trying to figure out.
Well, for now, I would say I'm very interested in what we just talked about. This is all very new, so I think I have a lot to learn about that, and we have a lot to do in that space still. But I think similar things to what we just saw with bus lanes, but with any kind of data, mobility, bikes, all of that, trying to bring all of it to a common base that could be the street, for example, would be awesome, would be a great challenge to work on.
Any other questions? Okay, I don't see any coming in. There's okay, so if there's no more, oh wait, hold on, we have another one from Eileen. I will unmute you to ask your question. Go ahead, Eileen. Wait, there we go.
Can you hear me?
Yes, we can hear you.
I was just wondering if, because every public transit agency is going to provide like different raw data and probably different variations of cleanliness in their data, do you feel like you have to customize the visualizations for each agency, or is there like a lot of overlap that you can use, like once you've sort of built it out for one agency, you could use it for another? Like how much extra work do you have to do with every new partner?
That's a great question, and I guess you work in this kind of thing as well, because yeah, that's exactly what happened. A lot of it, like I tried to create a process so that it could be reproduced easily. So a lot of it goes into putting the data in the right format to just put it into this pipeline that I created. Many agencies could bring the data or send the data in the perfect format. Some others very close. So there wasn't a lot of work on that. I shared with them some sort of standard that it could serve as a guide. But I would say that there is ad hoc work to be done for each of them. Mostly in the transformation and the cleaning of the data. Then the output, the visualization, also changes by agency, but it's much easier for us to change that visualization. Like it could be the cutoffs or the periods of time that they want to see, they want to split their data in. That kind of thing is much easier. The problem comes, when the data is very raw and you can find problems there. But we always try to make it so that we can use the same functionality for many agencies.
Yes, cool. Thanks.
Any other questions? Cool. So if there's no other questions, we can do our breakout groups. Yeah, I think everyone